We're going to be talking today about something that I touched on at the end of last class, which is this issue of dynamic decision problems. These are decision problems that involve uh, not only complex dynamics, where we might need a simulation model to help us understand the response of the system to our choices, to our decisions, or response of a system to external assumptions about factors outside our control. But they also involve ongoing uncertainty. Okay, not just uncertainty up front about some quantity, but uncertainty that's ongoing in nature, that involves uncertainty concerning external factors that might vary over time stochastically, like we saw how to simulate in any logic event sim last time. And problems of this sort also involve ongoing decision points. We're interested here in a situation where we have uncertainties unfolding over time, playing out over time, and where we have choices that can be made at any point or at different points along this continuum. So we're going to be talking today about the hybrid use of decision trees, and this is system dynamics models, which is going to be the particular example I've drawn on, but it carries over to other sorts of simulation models, all three types we've seen: system dynamics, agent-based, and the discrete event simulation. And I mentioned some of the local context of West Nile virus. West Nile virus being a very episodic burden within the province. Saskatchewan being distinguished in 2 years, 2003, 2007, as being associated with the highest incidence of West Nile in Canada. Indeed, I believe in North America for 2 years. But the remaining of the years having very, very low rates of low numbers of cases. So we're talking here distinction between hundreds of cases in some years and none in others. Sort of a feast and famine sort of situation where sometimes the burden is large, sometimes not. And I talked a little bit about the transmission cycle of West Nile last time, just as a reminder. While West Nile is a disease that's of concerns here for its impact on humans, humans are in fact dead-end hosts, so they don't pass on the virus to anyone else once they're infected. But they are infected by mosquitoes, and the reason mosquitoes are infected is because typically because they've bitten some reservoir species. In this case, what's shown as birds, which is believed to be the dominant one here in Saskatchewan, although there are others that are believed to play some role. So this virus circulates between mosquitoes and birds, and mosquitoes catch it from birds, birds can catch it from mosquitoes, and then there may be some transmission going on within each population, independent of biting of the others. So there's this kind of reservoir that builds up in birds. It moves back and forth in mosquitoes, and mosquitoes can bring it to humans. They can also bring it to other animals, such as horses, which exhibit sort of strong symptoms from West Nile, and were examined as so-called sentinel species to spot early emergence of the virus, although it seems they're getting it around the same time people are. So here people are getting it from mosquitoes, and one of the issues is that the mosquito life cycle, although it's involved, it has quite a large set of environmental dependencies that reflect the underlying processes. So adult mosquitoes, after drawing a blood meal, adult female mosquitoes, after drawing a blood meal, digest it, and they extract, as I understand, calcium out of the blood, and use that to form eggs, and then they lay those eggs in egg rafts, typically in an aqueous environment, I believe, in the water. And these egg rafts carry many, many eggs, and many of those eggs hatch and form larvae, and larvae remain in the water where they're predated on by other animals, including dragonflies, for example. They emerge into pupae, and the pupae remain in the water, and at some point they merge into the air and can become airborne and start to take blood meals of their own if they're female. The males, as I understand it, don't play a big role in this process of transmission. They don't draw blood meals from people, as I understand. So they just kind of flit around and interact with the females, but they're not part of the transmission cycle. So of course, when they're adults and they're taking blood meals, they may be taking blood from an infected bird, for example, or transmitting, in the process of taking blood from a person, they may be transmitting the virus that's already in their salivary ducts to a person. Okay? So it's this step of taking blood meals that simultaneously is how they acquire the virus and how they pass it on. Now, these mosquitoes, you'll note, are playing a role in two different environments, in the water here and in air here. And it turns out that they have really notable dependencies on the characteristics of that environment, most notably the temperature, but also the availability in terms of water surfaces in which to lay their eggs, in which to hatch and to go through their larval and pupal stages. So their dependence on temperature is the most notable one, and it affects things here at a couple of different levels. So it affects the number of blood meals that they'll draw, affects the amount of eggs that they'll lay, linked with the number of blood meals they're drawing. So if it's warmer, they'll lay more eggs. They will also, when drawing blood meals, tend to bite more often. So they'll bite a larger number of times for a single blood meal. They're more skittish, is my understanding from our provincial entomologist. It turns out that when they acquire West Nile through biting, it takes a shorter amount of time to propagate through their system and to make it to their salivary duct so they can pass it on. So the maturation of the virus within a given mosquito is more rapid with higher temperatures. Finally, it turns out they go through the larval and pupal stages more quickly with higher temperatures. So they develop more quickly. And the net effect is, with the impact on eggs, with the maturation, the quicker maturation at higher temperatures can lead to quicker intergenerational spacing times between within the mosquito population. So mosquito populations come closer together. You can have more mosquito populations in a hot summer than in a cold summer. And it's not a small matter, it's by a significant amount, is my understanding. So you might have 5 rather than 2 or 3, something along those lines, for a hot versus a much cooler summer. So you're getting this life cycle accelerated by temperature. You're also getting the virus within a mosquito maturing to a stage where it can be transmitted more quickly. And the end result is, in hot summers, there tend to be more mosquitoes, and there also tends to be a greater, quicker proliferation of the virus within those mosquito populations. So if you look at the mosquito populations, the prevalence of infection, the fraction of those mosquitoes that are infected at a given time, will tend to be larger with higher temperatures. Okay. Now it turns out that people too have temperature dependencies, something that we can measure with these sort of devices, for those who know what I mean. Within humans, human behavior varies with temperature outside. We are more likely to go outside when it's a pleasant day than an unpleasant day, and temperature is part of what makes it pleasant. It's not the only thing. Weather, in the form of rainfall, for example, can also make it more pleasant. turns out that people will not only change their indoor-outdoor division of time based on temperature, but it seems to be acknowledged, the commonsensical notion that when you're outside, if it's very, very warm, people may wear less. So they're less likely to wear long pants, long sleeve shirts, more likely to go around with flesh exposed that could be bitten by a mosquito more readily. So they're less likely to be protected. And they also, of course, will potentially have warnings given to them about the risks of West Nile. And their response to these may vary under different circumstances. Their sense of perceived risk may vary based on how many other people are getting infected or have been reported as cases, or severe cases that have been reported, how many people around them, how many people reported through the media. And their knowledge of West Nile virus and its risks may play a role some in governing their behavior. So we're dealing with a situation where we have a notable burden, which is caused in some years for West Nile, and other years almost nothing, where a lot of that burden is governed by, well, things out of our control, like the bird populations, and under limited control, like the mosquito populations, and where the dynamics of the spread within those populations is highly dependent on things that we can't predict, to wit, aspects of weather, aspects of temperature. And both human behavior and mosquito behavior are shaped by this, both for the worse, with higher temperatures. High temperatures seem to be the main culprit in 2003 and 2007 for that huge spike in cases. Now, this great dependence of the potential health burden year to year on temperature is a big challenge, because there's a need week to week within our health regions and more broadly within the province to make decisions taking into account uncertainties regarding the mosquito population, environmental conditions, and some aspects of human behavior. How cautious are people going to be? But particularly these first two. So we need to make decisions now about what we're going to be doing, say, over the course of the next week. Are we going to issue advisories? Are we going to start a practice called larviciding, which will basically kill off larvae in areas with a lot of human population nearby? Are we going to try to think about doing source reduction, which will reduce the amount of water available for mosquitoes for breeding? There's talk about vaccination here, which would be a longer-term strategy. But week to week, there's a lot of concern about what do we do, or do we simply wait? Now, here we're thinking about the mosquito population, which has some regularities. It's not going to instantly change by a factor of 2. It's going to vary in some way that reflects those conditions. And the West Nile virus prevalence is going to be changing within it in some structured way. At the same time, there are these environmental conditions which have shaped things till now, and which are going forward in a way we can't forecast exactly. We don't know exactly what will come out. And the challenge here is, what do we do week to week? Taking into account our uncertainties, taking into account where we are now, taking into account our uncertainties going forward about the weather, taking into account the fact that we will be able to, in another week, re-examine any choices. We'll be able to, in another week, think this issue through with an additional week of weather data, in hand. What do we do? Do we act now and try to head off big problems which could otherwise come about? Or do we wait and collect more information? Do we wait and collect more observations on the weather, etc.? So I argued last time that there's 2 different levels of challenges in dynamic decision making. And here we've been concentrating implicitly within this class on what I termed here, without any sort of broader implications to the terminology, type type A problems, where here we're trying to make complex dynamic choices given some anticipated sort of changes in factors outside our control. Either these factors don't have a big impact, or we think we have a pretty good sense of what a typical case would be, and we want to try to plan around that case. So here we're building models that help us understand the complex impact of our choices, to be sure, but we may confine our attention to sort of this expected case. That involves some tough challenges on the modeling side, but we have a certain amount of solace, or a certain amount of less worry, reduction in worry, because we're able to deal with this typical case. We're able to confine our analysis to a situation where we know about enough about the other factors to plan with confidence. But here, for West Nile, we are solidly in this case of type B. And I think actually a lot of the conditions we've discussed in this class are actually more type B problems. So here we're trying to make complex dynamic choices, and we need a model to help us understand the complex impact of our choices. Fair enough, and to look forward given where we are now. But the problem is that we have a real dependence of how the system will evolve, how our simulated system will evolve, on factors that are outside our control and could vary really widely, could vary in ways that we can't exactly anticipate, and where it's not safe to simply plan around some expected course, some typical case. We can't, for West Nile, simply say, well, we'll do West Nile planning based on the average temperatures through the summer. That doesn't cut it, because the average is not representative of the, if you look at the average, that might involve a very small number of cases of West Nile year to year. But if you actually look at what goes on, perhaps most years you have very few, but some years you have a very, very large number. And the averages over the mean, as it were, if you look at the distribution of cases, may be much, much larger than just dealing with the mean temperature and what comes about through the mean temperature, because it depends non-linearly on the temperature. The number of cases may rise quite dramatically with the temperature, and so you may have something like this with the mean summer temperature. And if you do, dealing with the mean temperature might give you something along these lines. But if you actually look at, you consider sort of, okay, there's some hot summers and there's some cool summers, maybe you'd actually find the outcome of the mean outcome, take into account that distribution, would actually lie, instead of lying here in terms of number of cases, mean cases per summer, would actually lie up here. Okay, it would actually be, this would be the mean sort of number of cases per summer, taking into account the variability of temperature, whereas this one here, this much smaller value, is if you just plug in the mean temperatures for the summer, okay, and just work with that. This is a nonlinear function, so the mean of the function of the mean of the underlying distribution, the function of the mean of some underlying distribution, in general here, is going to be less, this is superlinear, so it rises more than linearly, less than the expected value of the function applied to each member of the distribution in turn. Okay, so if you apply this to each member of the distribution, there's going to be some cool summers, some hot summers, and you take the number of cases from each of those and you take the mean of that. This in general can be quite a bit larger than this, quite a bit larger than just plugging in the mean value and saying, let's take the number of cases for the mean temperature. So here, we're trying to deal with a situation where we have big uncertainties. We can't just deal with the average case, the typical case. We have to instead deal with the variety of cases that are possible. And more than that, though, we need to plan on an ongoing basis, week to week, to make decisions based on that. We need to take into account what our current situation is, what our anticipated situation going forward would be, to make decisions now. But we also want to take into account the fact that we're going to be making decisions again next week. And we could choose to not make a choice right now, to undertake anything right now, knowing that next week we may have more information and can therefore make a better choice. Okay. So in contrast to type A problems, where we can work with a preset plan that we identify optimally ahead of time, we say we'll look at the typical case, we'll identify the type of plan that's best. This is how we handle these situations based on the typical case, and we've identified our optimal plan. Here, we're instead talking about avoiding putting all our eggs in one basket, avoiding betting that we're going to get the typical case, avoiding betting we're going to get the average case or what have you. And instead, we avoid a preset plan and we try to adaptively make choices over time. We don't use a preset plan that's one size fits all for all summers. Instead, what we do right now will depend on what has been observed in our current state as best we can measure it. So rather than sort of going in and saying the best strategy for West Nile is to do this on this week, this to do on that week, that to on that week, regardless of the temperature. Instead, we're going in and making a contingent plan, a plan whose decisions will be explicitly conditional on where we're at and what we've seen in terms of temperatures. Okay, where we're at, I'm talking in terms of estimated mosquito population right now, estimated prevalence of mosquitoes among the birds, etc. Okay, so with these adaptive decision problems, we're trying to make decisions now where the choice of the best decision depends so much on what plays out in these things beyond our control. Temperature trends, precipitation, prevalence of infection, and migratory bird populations. We don't have control over those things. And so much of the implication of our choices depends on what these things are that we need to observe them. And the question here is, how do we make our decisions now despite these uncertainties? Should we wait and see how things are trending before making decisions, or should we choose now and try to head things off? So these adaptive decision problems have certain characteristics. We can't count on one particular future trajectory. Choosing things now requires considering how things might unfold, the many ways in which they might unfold explicitly. We have to make these decisions over time as things unfold, and we can always defer a decision until we have more information. And that will allow us to collect additional information, but it will defer the opportunity to make a difference too. So it may be advantageous to desire to wait and see, as to see how things play out. Or in some cases, the ability to intervene early may have a disproportionate impact. I should mention here that West Nile is one of those issues where early action is very important, and that's one of the things that makes this dilemma all the more pertinent that we're dealing with. So by the time there are significant human cases for West Nile, it's very likely too late to do much about them. There's not too much you can do by that point because you're seeing a lagged indicator of infection. In other words, if you're seeing human cases, chances are there's a bunch of other people out there who are infected, and they just haven't presented yet. And you could go even do adulticiding, which is a type of sort of more drastic intervention that has been undertaken once you're in the province, but it involves fogging the mosquitoes at night, and it's of concern for people with reactions. It's of concern for its potential implications to broader human health. And you could do that sort of fogging against mosquitoes, but the cat may be out of the bag. In other words, people may already be infected, and so you could fog the mosquitoes and so on, but that's not going to prevent the damage that's been done. So in these conditions, we're trying to make a decision, and it depends on certainly our current situation. What do we observe? What's our best guess for how many mosquitoes there are out there? What fraction of them are infected? What have we observed to this point? Has it been a hot summer so far, right? That's relevant. That would have contributed, to be sure, to mosquito numbers, but also to some degree to the proliferation of virus in the mosquitoes. So we have some sense of those through our measurements, but also to human behavior. We want to also take into account past or future eventualities. given that it's a hot summer, is it likely to continue as a hot summer? What are the weather forecasts saying? What do we anticipate about how the mosquito population will grow given where it's currently at? What's the temperature right now? Because that's going to be affecting the maturation of the pupae and larvae still in the water right now. And of course, we want to, again, take into account the fact we have ongoing decision making. We're not trying to decide now for all posterity, what our decisions are going to be. We're trying to decide what we do now that will influence our choices over the next week. And we're going to revisit it. Okay? So we're balancing two desires here. Seizing the moment, acting early, the whole adage of a stitch in time saves 9. We may be able to head off a lot of problems by intervening quickly, early, before, and nipping it in the bud, getting it before it's out of control. And secondly, a desire to wait and see. Let's wait and see. Let's get more information, see what the weather does over the next week, and then decide on the basis of that. These pull us in two different directions. So we're going to be talking today about a hybrid system that combines, on the one hand, simulation modeling. And again, this could be agent-based, system dynamics, discrete event, simulation model with a decision tree. And the decision tree here is going to be responsible for representing the events and choices over time. And it's going to then tell the simulation model about those. So the simulation model does the job of simulating the consequences of those events and decisions over time. So the decision tree is going to be basically systematically structured so that we can examine the impacts of different combinations of events and decisions over time. And it's going to tell the simulation model, okay, assuming this pattern over the course of the summer of events and decisions, go off and evaluate it. How many human cases will there be? How many severe human cases will there be, etc. Go off and do that and tell me the consequences. And I represent them in the decision tree. And then I use the decision tree for helping me gain insight as to which decisions might be most desirable at different points in time. But first here, to help you understand this, I need to explain decision trees. So I'm going to go in and have a little introduction to decision trees. Now, decision trees you could view as a fourth major sort of decision of model within this course. They're not a simulation model, but they are an extremely useful and moreover an extremely widespread tool for making decisions, ongoing decisions particularly, in the course of ongoing uncertainties. They're widely used in health, among other things, but they're also used elsewhere. They're used in certain areas of AI, for example, within computer science, for representing decision problems. You'll see them very widely used in the management literature for in the context of business management, for example. And in general, they're a very, very easy to deploy, handy tool for thinking about decision making when you in the context of ongoing uncertainty. Okay? Particularly ongoing uncertainty, even static uncertainty, they can be quite useful. So decision trees in this context can be used for two real big purposes. One is for illustrating decision making in the context of uncertainty, sort of mapping out the possible choice space, the policy space, as it were, an uncertainty space associated with our problem, and they're very useful diagrammatically. The second thing is quantitative reasoning, helping us make better choices in light of these set of decisions and events we have over time. So these decision trees represent flow of time, choices, we call decisions, uncertainties, we'll use the term events associated with these uncertainties, things we can't control, things that are uncertain to us, and consequences, the impact of a sequence of decisions and events over time. What does that give us in terms of its consequence? So decision trees, like the other sorts of models we've seen, come with a sort of graphical language. And in fact, this graphical language is very, very widespread. So if you go and you look at decision trees in these different fields, you'll find them using a common vocabulary in terms of the semiotics of it, the use of symbols and their implications. And there's a variety of decision tree packages out there. TreeAge, Crystal Ball are two examples, but there's quite a few others that are popular. They all, however, support a basic set of components, and then some additional ones which I'm not going to talk about here. So if you go look at TreeAge Data, for example, which is a fine package I've used quite a bit, you'll find that they have additional sorts of nodes, which aren't shown here, but I'm concentrated here on the basics. And really that's what we need for our integration that we're talking about. So on the one hand, we have a decision node. This represents a decision node. It represents at a particular point in time, that's important, a particular point in time, you have a choice. Choice A, B, C, or D. Say 1, 2, 3, 4. Those are your choices. A chance node, by contrast, represents some uncertainty. Again, at a certain point in time, there's some uncertainty about what will happen. In contrast to a decision node, where you have a choice between different factors, so you could choose which you will undertake. In a chance node, you don't have control over what will play out. That's beyond your control. This might be, for example, high temperature week, medium, and low. We can't directly exercise control over that, but we may be able to assign a probability associated with that, a certain probability of occurrence of that event. Okay. And indeed, with event nodes, chance nodes, we're required to assign probabilities to each of the outcomes, and those probabilities must sum to 1. Okay, so we may have some possibility 1 with 50% chance, 2 with 30% chance, and 3, there's a dot here, with 20% chance. So they collectively sum to 1. So one of these eventualities will happen, we just don't know which. Okay, and the final type of node is what's called a terminal node, consequence node. And it's associated with consequences of a series of events and decisions over time. And so this is an example, and I apologize, this isn't drawn for the domain area, but I've used these in my undergrad software engineering course as well. And this may speak to some people in the class as much as any health example. Here we have a decision tree which represents an initial choice and then some uncertainty and then some consequences. So for example, we may have a software project and we're trying to figure out, there's a new version of an OS that's come out, and it has some new features in it, or maybe it's a new version of Java 7 that comes out, and we are wondering, should we depend on certain things in the new Java virtual machine that it supports? I should say it's anticipated to come out soon. If we do put into place a dependence on this, it may simplify our software development. It may allow us to make use of a fancier interface, a nicer user interface. However, it also does expose us. If we rely on it, it will gain us something if it ships on time. But if the new OS is delayed, if it turns out that this new operating system that we're going to ride on top of, that we've crafted our system now to ride on top of, if it's delayed, we could stand to lose some money. Okay, so we've got to make a choice now as to whether we want to rely on these new OS features and potentially reap the benefits of greater sales because we have a nicer user interface, or do we wish, but at the same time leaving us vulnerable to a delay, or do we wish to simply not rely on the new OS features? In this case, this is our baseline, so we have a net change from our baseline of 0. This is a net gain of 50, but it's more likely to occur. 50,000, this is a net loss of 200,000 estimated, but it's less likely to occur. So here we've mapped out a decision problem. We have to choose now, and there's some uncertainty that's involved with an outcome of one of the choices, and we'd like to make a better choice. You notice these consequences here, this minus 200,000 or this 50,000. Each of those is a consequence that reflects the set of decisions and events over time prior to that. So this 200,000, that means we lost $200,000 by making the choice to rely on the new OS and then it's been delayed. So it's in light of that series of things which played out, some under our control, some not, we've lost $200,000 compared to the baseline. Here, we've gained $50,000 because we've seen a certain set of decisions over time and events over time. So, we did decide to rely on it. The new OS did ship in time, and so we get better reviews perhaps for our product. We get better word of mouth. It spreads more quickly, and we secure greater proceeds from the marketplace for our software. So here we have this potential trade-off. By making this choice, we leave ourselves exposed, and this decision tree is going to help us reason about this. So the process to help us reason about this is something called rollback. It uses a technique called rollback to calculate the decision rule that's termed optimal in light of what you've represented. What we do here is we're going to systematically evaluate this tree so that for each decision point in the tree, if we reach that decision point, here we always reach it, but many trees we may have contingent decision points that aren't automatically reached, but if we reach here, it's going to give us a recommendation for which of these is the better choice. Okay, so if we're here, which would be a better option to choose in light of the expected gain here in terms of money. Okay, so which of these would yield us a larger expected outcome? So there's a very simple process for doing this. So for terminal nodes, so basically it involves assigning a value for each successive node of this, but doing it from the bottom up, from the leaves up. And it's a very simple sort of linear algorithm, linear time algorithm, linear in the number of nodes of the tree. And basically we're going to start at the root, at the leaves of the tree down here at the terminal nodes or consequence nodes, and we're going to assign value. So we have values for these that we've already figured out, and then we're, on the basis of this, we're going to work towards the root of the tree, calculating successive values at each node. Okay. Now, how we assign the values at the node is going to depend on the node type. For terminal nodes, their value is just the consequence. That's all there is. For event nodes, we pass up the expected value of the children. By expected value here, it'll be, this is 10% chance of occurrence. It has minus 200,000, so it'll be 0.1 times minus 200,000 plus 0.9 times 50,000. That make sense? Okay. And that would be associated with this node here, right? So here I think it would be a net gain of 25,000, I believe, right? So this would be minus 20,000 so if we multiply this, the component of the expected value coming from this is minus 200,000 times 0.1, which is minus 20,000, right? Here, 0.9 times 50,000 is 45,000. So you add them together, 45,000 minus 20,000 from this is 25,000 expected value here. And for decision nodes, which is the remaining one, we're going to select whichever child offers the highest value. This is a case where we have a choice. For event nodes, we don't have a choice of what the outcome is, so we have to deal with all possible outcomes. We have to deal with, well, we could have this outcome or that outcome, so we're dealing with an expectation. 0.1 of this, 0.9 of that, we have to take both into account in our value for the event node. Hence, we have to take the expected value of their outcome, of the outcome. For decision nodes, we have our choice. We can choose the one which is more desirable. So we're going to select whichever child offers the highest value. Whichever child is better in general, because sometimes you're dealing with things where actually less is, if you're dealing with cases of West Nile, you'd prefer the one that's smaller. But here, we choose whichever child is better, and we pass up that value. Okay. So here, we're going to have, again, from this expected value, we're going to have 25,000 here, 0. And so what this is saying is it's preferable here for us to choose this one of relying on the new OS features. Now, this is in strictly monetary terms. The expected gain from relying on it is larger than the expected gain for not relying on it. Obviously, that's going to depend on these values here, 0.9, etc. So if this changed to 20% chance the OS is delayed, that might change our calculation. Actually, I think in this case it wouldn't, but it would bring us much closer to parity. 30% would change the balance. So here we have a situation which is contingent on these probabilities, and indeed this is something we can examine in a decision tree. Another thing that we may wish to examine is, we're doing this in a strictly monetary way. The expected gain through this is higher than the expected gain through that. But we may also wish to take into account risk aversion. We may have a preference function which says basically gaining $10,000 is, for example, gives us less net change and desire and satisfaction than what is associated with losing $10,000. In other words, losing $10,000 is a lot worse than gaining $10,000 is better. It matters more if you're losing it than gaining it. And you can represent these things through preference functions. You could represent the fact that losing $200,000 is inconceivably bad, and losing $50,000 is great, but it doesn't even compare to losing $200,000. This might drive us out of business, where this would help us expand as a business some. And if we really, really want to avoid this, if this is catastrophic, we could use what's called preference-weighted outcomes. And there's a theory behind this. And this theory actually is tied in the health sciences with things that are called health utilities indices, for example, for measuring quality of life associated with patient state. So there's an underlying theory here associated with utility scales and preference functions that comes out of management science. And I was tempted to put that into here. It's really interesting. It's one of the reasons that if you understand it, you start to understand a whole bunch of things which otherwise may seem puzzling. Like, why do people pay insurance? In general, when you pay insurance on a house, for example, you're losing money for the typical case. If you look at the expected value of your gains through insurance, it's negative. So why do people get insurance? It's because they have a preference function, which you could view it as them having a preference function which, in which loss of the house is inconceivably worse than, the loss of just some money associated with paying an insurance premium. And so they'd much rather, they're risk averse. They'd rather avoid loss of a big thing like that than, and pay a little bit, than on average lose a bit of money than they would, to on average be better off but have the risk of this big outcome. So there's a whole science associated with preference function elicitation and describing preference function in decision trees. And suffice it to say that it's actually quite practical, and you can use it to capture risk aversion, or for that matter, risk neutrality or risk loving sort of attitudes. So I didn't go into this in this particular subpiece, but this is an area with substantial additional components to it. So here we have, within our decision tree package, we can ask it to evaluate these things, and a decision tree package will, for example, indicate for us, associated with each node, what its value is through this rollback. This is a so-called rollback procedure, also called backwards induction. And what this is telling us is rely on, that this choice here, this $25,000 choice, is the preferable one in light of our sort of the what's in this tree, the assumptions in this tree. Okay, so here we can have a decision tree which involves multiple stages over time, and we're going to see this in spades. This is a very simple case. But the key thing to realize, again, is that time is running this way along the lower, along the x-axis, so time is increasing to the right. And here we have two sets of choices over time. So one set here and one set later, contingent upon something happening. So here this relates to if we're counting, for example, on a new OS, and the new OS is delayed. Well, Do we ship and hit the market sooner without the final release of the OS just going against the release candidate? Or do we actually wait for the OS to finally be shipped and test fully before shipping our product? So here we have a decision, and what's very important to recognize about this later decision is it's contingent. This decision doesn't come into play if, for example, we decide not to rely on the new OS features. Or indeed, if we do decide to rely on it, but the new OS ships in time, we never get to this decision point. This decision point is not an issue. But if we do get to this decision point, through rollback, we'll get a recommendation of which is better, which choice is better. Okay. Okay. So when we're dealing with these decision trees, we're trying to identify for each decision point in the tree, each decision node, we're evaluating a most desirable outcome, a most desirable choice. Now, those choices, in general, the presence of those choices, what we decide at this point, will often be contingent with what's going on before. Sometimes we'll have the same decision, essentially, conceptually the same decision, which needs to be made at the same point in time, and what we'll decide will change based on what's been observed. We may represent it in multiple nodes here, but it's the same fundamental decision. Let me give you an example here. So here we have choice and decisions over time. This example drawn from some consulting I did many years back involving investments in infrastructure. And we have an initial choice about whether to expand our infrastructural capacity or not. And the impact of that initial choice will depend on the level of economic growth experienced in the region. So if we decide to expand capacity, that could really pay off if we have high early growth in the region. But it may go underutilized. It may not confer much benefit if we have low early growth. Conversely, if we decide no expansion, if we have high early growth, well, that can start to really put pressure on our resources. On the other hand, if we have low early growth, that might be just fine. We're in a situation well suited to our infrastructure that's in place. Now, later, this is now years later, with time running down here to the right, we have a choice to revisit our decision. Okay, are we going to now invest in infrastructural capacity? Should we expand our capacity or not? You could think of this as expanding, say, telecom capacity, right? And its outcome has been contingent upon the desirability of expanding that capacity. It probably depends on how much demand we're actually seeing for our fibers. Has internet growth really, has the use of the internet as a platform for delivery of streaming content really grown as per our expectations, etc. So here we have another choice, and notice that it's the same choice, top to bottom, for this later point. This is the same choice, top to bottom. Do we expand capacity or not? And what we do here is generally going to be contingent upon what's occurred earlier. So, for example, what we do, whether we expand capacity now, it kind of makes sense if it depended on, for example, what have we experienced high growth to this point? Did we expand capacity earlier? For example, even if, suppose we didn't expand capacity early and we saw high early growth, we might really need to expand capacity now. By contrast, if we had not expanded earlier and we expanded low growth, we still might need no expansion now. So here we have these decision nodes and these event nodes over time, and these consequences, to be sure, from each of these. We have a particular scenario here, a scenario, for example, that may play out where we make an initial choice, no expansion, we have high early growth, we decide to expand, and then we have low later growth, and then we have some consequence that comes about because of that. That would be one scenario, right? But in general, we have to start thinking about decision rules. to identify a rule. A rule will basically specify what we should do given any possible eventuality. And here's, for example, a static decision rule. We can have decision rules of two different sorts: one dynamic and one adaptive and one static. Here's a static decision rule. I will simply say it to you, and we'll see how it's represented. The decision rule is we will not expand capacity now, and we will expand capacity later. That's going to be our plan. We're going to decide it now, and we're going to stay the course. We're going to stick to that plan, no matter what happens. So we're first going to have no expansion, then we're going to have a later expansion. Okay? So the initial expansion here is shown through, the existing non-expansion, the fact that we're sticking with no initial expansion is shown through this. And then, regardless of what happens here, whether we have high early growth or low early growth, we're going to expand capacity subsequently. Yes? Yeah.
I'm just wondering, how do you assign probability of the event? Is it an arbitrary way or just much better than that?
This is a good question. So, decision trees are typically used with events which are where the type of events that could occur is known, so you can map them out as children of the tree. In terms of the probabilities, they're often subjectively estimated. They're roughly estimated as being in some range, and then what you do is you examine the impact of changing that. So you examine the sensitivity to changing those assumptions about the likelihood of something occurring. And often it's hard to have a really objective way to estimate the probability of that event. And trees are very regularly put together with just rough estimates of probabilities put in there, taking into account what you know and your best guess for what that probability is. And then you'll do a sensitivity analysis I'll show you, which will examine, maybe I'll show it right now, that will examine, so for example, if I assume this value for probability of the OS being late, or this probability for a bug having crept through my testing, what does that tell me about what my choices should be? Okay, what does that tell me about what my choices should be at a certain decision point? So for one region of the space, for example, if there's a high probability the OS is late, or there's a high probability that there's a test escape. There's a bug, a defect that's escaped through your test processes in your software. So software goes through testing before shipping. Good software goes through testing before shipping. Among other quality assurance processes like peer reviews, etc. And so if there's a good chance that your testing has not been thorough enough, and there's actually ways to estimate the number of undiagnosed bugs out there and so on. If there's either high probability OS is late or high probability you may have missed something, then this is telling you don't rely on the new OS features. Otherwise it's saying, what's best for you is relying on the new OS features. So these here on the X and Y axis are probabilities of different things occurring. And so they're assumptions about the probability. And what this is saying, for example, is we may be uncertain about the probability OS is late, but we all agree it's less than 10%. If no one in our company agrees that it's more than 10%, then really it doesn't change our decision. So we can argue till the cows come home about the exact value of this probability, but a rough subjective probability, as long as everyone agrees it's less than 10%, it basically says, okay, yes, let's go ahead and rely on the new OS features. Does that make sense? Yeah. Yeah.
I was just going to make a comment that while we won't turn that off, and there certainly are examples of decision analysis and decision trees in different places
Mm.
that are based very
That's true.
highly, probabilities are based very highly quantified. So
Good point.
There are some examples where
Very good. Thank you, Cheryl. Yeah. So I worked quite a lot with decision trees with people from business science, and they're often the evidence base is far less because you're dealing with a very fast-moving environment where probably no one's done close studies of things before. There are some things they might have. For example, you may have historic estimates for test escapes, like you know, the likelihood bugs of certain levels of severity will make it through your testing processes. You may be able to assign a better number for that. But Charles, exactly right. One of the big uses of decision trees, actually, in the health sciences side, is at clinical level reasoning, for example. Should we give this drug or that drug, etc., and or this treatment, this procedure? And there's often a fantastic evidence base, and you can leverage very well estimated procedures. Or very, very well estimated probability. So thanks, Charles. That's very valuable comments. Okay, so we talked about decision rules. This is a static decision rule because I'm doing the same thing. I'm making this choice. No expansion up front, expansion later, regardless of what's coming up. I'm saying I don't need to worry about the vagaries of weather, well, no weather here, sorry. Vagaries of industrial growth, whether we have a really big, you know, boom time in the next 5 years or whether it's modest. I'm going to make the same decisions, right? That's a static decision rule. It's a decision rule that does the same things regardless of what happens. And we call it a decision rule because it tells us not just what to do here, but not just what to do at a single decision point, but what to do at each decision point that can be reached here, right? That's why it's a decision rule. It says, if this happens, do that. If that happens, do this. Yeah? By contrast, here's an adaptive decision rule. Okay, no expansion up front. That decision has to be made up front, so there's no issues of things. But this is saying, okay, if there's high early growth, then I will expand capacity. If there's low early growth, I won't expand capacity. This is a contingent decision rule. Here, my choices are contingent about what's been observed, right? I can't simply say, you know, for this rule, what to do ahead of time without mentioning, well, if you see this, do this. If you see that, do that. This is contingent. It's conditional. It depends on observations. And, you know, to evaluate these two, we could do we could do appropriate evaluation of the results. So to evaluate, say, this decision rule, if we wanted to, we could do a rollback here, take into account that we're definitely making this decision, for example, do a rollback and evaluate the benefits here versus this one. We could do a rollback along these particular paths and evaluate this. Now, you notice with this decision rule, there are certain things, whether it's static or adaptive, there's certain underlying essentials of this decision rule. I mean, we have no choice at this point. This is an event point. It's not a decision point. It's an event point. And we have no choice what event we occur. We have no control over whether there's high levels of economic growth and low. That's not under our control. And so we have to handle both outcomes, right? We can't choose one of these. Decision point we can choose. That's part of the decision rules, choosing a certain thing at this point. Here, again, we have no choice. It's an event point. So we have to be able to handle both of those. Okay? Okay. So, so decision rules specify what we should do given any possible eventuality. So here we had this decision rule. If this went this way, we had to be able to say what we were going to do. If this went that way, we had to say what we were going to do. Of course, we chose here, so we don't have to specify all this. But these are things we don't control, so we have to specify for these guys what we're going to do. Does that make sense? Okay. And decision trees can be used to identify optimal decision rules. That's going to come out of our rollback, is our identification of the optimal decision rule. And of course, this is in light, ladies and gentlemen, of our simplified assumptions. You know, this is in light of what we've encoded in the tree, and our assignment of probabilities, and our assignment of consequences, and the fact that we're only representing certain things and not the tree and not in the tree and not others. Okay. So a static decision rule here pursues the same predetermined set of decisions, actions, regardless of eventualities, regardless of what's coming, been observed in terms of events. We're doing the same thing. An adaptive decision rule, by contrast, varies its decisions based on which events have occurred. Now, the observation here is that static decision rules, ladies and gentlemen, are rarely optimal. So in other words, while static decision rules will get us a certain distance, while pre-planning what we're going to do, no expansion and then expansion, while pre-planning something like that and staying the course will get us a certain amount of benefit on average. If we want to secure a really large benefit, it's likely that the greatest gain will be from an adaptive decision, one that observes this. And this is something which has been noted in the decision science literature for decades. Adaptive decision rules tend to yield more favorable outcomes. They're rarely optimal. Okay, so turns out that decision trees provide us the mechanisms we need to evaluate, to identify the optimal decision rule, and to indeed evaluate possible decision rules. And it turns out that we're going to only be touching on just a little bit of this here. You can add symbolic components to these decision trees, and indeed packages like TreeEdge do this, to greatly expand the power. And those allow you to conduct the sort of sensitivity analyses we just saw, that I showed in response to Yemi's question. So you can do strategy selection, one-way, multi-way sensitivity analysis. You can do what are called value of information analyses, which are very, very powerful sort of analysis, which allows you to say, if we could know with greater precision, for example, what is going to occur at this point. Imagine the case of West Nile. If we had access to better forecasts, better weather forecasts, for example, or if we had access to better diagnostic technology so that we knew with greater certitude whether someone was in a true West Nile infection case or not, or if we could know with greater certainty, for example, the level of prevalence of West Nile among mosquitoes, how much would that help us make better decisions? And what would that ripple through to in terms of our savings by making better decisions? It may be worth it to pay for extra information sometimes because it improves the quality of our decision making and therefore secures us net benefit in terms of our savings. It may cost us something to pay for it, but it'll save us more money because of we can do things more intelligently. Value of information analyses, value of perfect information analyses will let you gain insight into that. Here's, for example, is a decision tree with variables, and this is a sort of analysis you can do in packages like TreeEdge. Yeah, this is drawn from my undergrad course, so I should have customized it. But suffice it to say that decision trees can be used. What we're concentrating on here is sort of, I won't quite say impoverished version of decision analysis, but it's really simplified for the sake of compressing into a lecture. In general, we're going to have trees which span not just one consequence, where we don't just have a single consequence at the end here. We may have multiple consequences. And this gets into the area of what are called multi-attributed decision analysis and decision problems. So we may care about multiple attributes. So in terms of something like West Nile, we may care about the number of severe neurological cases, but also something about cost. We may wish we may care about one at a higher priority level than another, but all the things being equal, we'd like to lower costs, for example. Maybe because we have some limited pot of money, and there's an opportunity cost. Putting the money into this, for example, will take money away from something else that could save lives elsewhere. Save lives through better treatment of diabetes, or lower burden of influenza among the elderly, or what have you. So when we're dealing with limited pots of money, we really need to think about opportunity cost, and cost, therefore, does come into the equation in a big way. We want to get the biggest bang for our buck, biggest gain for our costs. And so we may want to think about costs, severe neurological cases, also the number of severe West Nile fevers, maybe, could be an issue. We may wish to minimize environmental impacts of our interventions. Terminal notes and decision notes can actually capture multiple attributes, and in fact, in triage, for example, you can put in different outcomes for different attributes, and you could have preference functions that sort of balance these in different ways, and it's actually quite powerful, and lends itself to integration. So here, ladies and gentlemen, what we have is a situation where we can marry the best features on the one hand of decision analysis with the best features of simulation modeling. In the West Nile case, Karen here has been working on a situation where we have a decision trees representing West Nile over uncertainties and decisions involving West Nile, and we have in this case, a system dynamics model. This could be again agent-based or discrete event simulation model, where we have which is capturing the regularities involved. So there's big uncertainties, but there's also big regularities. Mosquitoes multiply at certain rates. Given temperatures, a certain temperature profile, it needs to affect a bunch of different things along the mosquito life cycle and the maturation of the virus. And there's structured interaction between birds and mosquitoes on the one hand, and between mosquitoes and people on the other. These things can be described, characterized in models at whatever level of aggregation. And those models can be used to evaluate, ladies and gentlemen, the impact of a sequence of interventions and temperature profiles over time. And to tell us what the implications are for a number of West Nile cases or what have you. Okay, so let me see if right, so let's talk about this hybrid approach. The hybrid approach is aimed to have this ongoing process of observation decision making, captures these uncertainties in the decision tree, and it simulates a broad range of possible futures, possible, say, temperature variation over the course of the summer, not just a single scenario. We're talking about running the simulation model against a wide range of possible scenarios involving, on the one hand, temperature changes, and on the other hand, decisions associated with them. We have staging of decisions at different points, including the decision to wait and see, to exploit further options. Okay. So this is the division of responsibilities, the essential division of responsibilities here. Simulation model is responsible for some things, and the decision tree has its own bailiwick responsible for other things. Simulation model here is designed to calculate the dynamic consequences of a sequence over time of events and choices. Okay? So its job in life is to accurately capture the impact if you assume a certain temperature at each different week of the summer, and you tell the simulation model, assume this temperature this week, this temperature that week, that temperature that week. Basically, the temperature profile over the course of the summer. And you give it, and you say, I will have, advisories at these weeks, and I will have larviciding applied at this level and this week, and then that's all for the summer. It will give you an estimate of the number of cumulative West Nile cases at the end of the summer, or cumulative West Nile severe neurological cases. So the simulation model basically doesn't have to worry, ladies and gentlemen, about the uncertainties, about the range of uncertainties or the decisions. It's just told for particular decision sort of points, the decisions to be made, and a particular set of assumptions about the uncertainties, go off and calculate. And it goes and calculates. Okay? Goes off and does its thing. And it basically comes back and says, if you had that sort of profile of temperature and those sort of interventions, these are the number of West Nile cases that I'd expect. Okay. The decision tree, by contrast, needs to front and center represent the uncertainties, the set of uncertainties and decisions and their points in time. it gets its consequences from the simulation model. And it basically takes care of capturing all the uncertainties and representing the policy space. Okay. So here for the West Nile, simulation models responsible for representing mosquito life cycle, bird life cycle, transmission between mosquitoes and birds, human infection and disease progression. And in the future, we'll probably put a costed resource use components, quality of life. Decision analysis, a decision tree in particular, is responsible for the decision options over time, uncertainties, and consequences, for representing these consequences obtained from the simulation model. So here's the large parts of the West Nile system dynamics model, and here's a decision tree. This decision tree in general would, for realistic application here, would be much larger. We'd have many additional weeks because we're dealing with the span of a summer. But we have a set of decisions which would involve a similar set of possible choices for different points in time. Okay? And way down here in the terminal nodes, that would be the consequence of a given sequence of decisions and events over time that lead from the root up here of the tree, that first point in time, down to the terminal node. That's that sequence over time of choices, interventions, which may include wait and see, do nothing, and events, temperatures that occur at different points of time prior to this point. And this consequence would summarize it for the entire summer. Would summarize the consequence in terms of number of estimated cumulative West Nile cases that apply, or would likely be generated by this. Okay, and the idea here would be to use this system to then do a rollback. So here we have the system dynamics model simulating each of these consequences, giving its value to them, lending it a value to them for each consequence, and then doing a rollback here, so that at any given point during the summer within this tree, say if we're on week number, well, this is week 2, but it could be week 15 or what have you. If we're here and we've seen, by implication, we've made these previous decisions and we've observed these things, what should we do here? What's the recommendation? This is a decision rule we're trying to identify. For each of these decisions, if we reach there, what now? What choice should we make to best minimize, in this case, the number of West Nile cases? Later we could take into account the cost side or what have you. So all along here we are trying to make intelligent choices. We're trying to identify the best decision rule. And this combination, on the one hand, of a decision tree, on the other hand, of the simulation model to fill in each of these values, will allow us to do that. So next time, we're running out of time right now, but next time I will show you the system that was built by one of the graduate students here, to populate this tree automatically. So basically, the software goes off, gets a description of the decision tree, actually generates it optionally, and it will then go through systematically for each of these nodes. It will go off and run the simulation model for this particular sequence of choices and events over time, and it will assign it a value. And it will go down systematically through these, assigning each of those values. And these could be 10 nodes, it could be 100 nodes, it could be 1,000 nodes, or it could be 10,000 nodes. Running the simulation model for each of them, automatically populating it, and then allowing you to do the rollback to give you that sense of sort of what to do at each particular point in time. Okay, so that's the basics of it. We will finish up this discussion next time, and then probably go on to talk about calibration-related issues. Okay, so that's all. Thanks very much.